Black hole bomb becomes reality. Experimental validation of super-radiant energy. Extraction for decades, black holes were regarded as enigmatic cosmic entities that absorbed everything crossing their event horizons. Nothing, not even light, could escape their immense gravitational pull. However, starting in the mid-20th century, theoretical physicists began to reconsider this image. New models suggested that black holes might not just be passive consumers of matter and energy, but dynamic systems capable of energy exchange. One of the earliest and most influential contributions to this idea came in 1969, when British physicist Roger Penrose proposed a mechanism that would later become foundational in our understanding of black hole energy dynamics. Penrose theorized that the region surrounding a rotating black hole, specifically the ergosphere, could allow for the extraction of energy. In his model, particles entering this zone could split, with one falling into the black hole and the other escaping with more energy than the original particle possessed. This process, known as superradiance, hinted that rotational energy could, under the right conditions, be tapped from a black hole. Over time, this concept evolved into something even more intriguing: the theoretical construct known as the black hole bomb. The idea was further developed in 1971 by Soviet physicist Yakov Zeldovich, who proposed a way to test Penrose's theory on Earth. Zeldovich suggested that if a rotating conductive cylinder were exposed to an electromagnetic wave matching its rotational frequency, the wave could be amplified by absorbing energy from the spinning object. This process would serve as a terrestrial analog to the super-radiant behavior theorized in black holes. A year later, American physicists William Press and Saul Tucholsky expanded the model. They theorized that waves entering the ergosphere of a black hole could bounce back and forth, if there were a reflective mechanism, and be amplified with each pass. This feedback loop could, in principle, extract large amounts of energy from the black hole's spin. In extreme cases, the process could grow uncontrollably, leading to an explosive energy release, thus the term black hole bomb. For over 50 years, this concept remained a topic of purely mathematical and theoretical exploration. But in 2025, a groundbreaking experiment at the University of Southampton in the United Kingdom changed that. A team of researchers successfully created a laboratory analog of the superradiance effect, marking the first time this phenomenon had been observed under earthbound experimental conditions. Their approach was both elegant and innovative. At the heart of the setup was a rotating aluminum cylinder with high electrical conductivity. Surrounding it were 3 layers of copper coils integrated with RLC circuits. Importantly, there was no direct physical contact between the cylinder and the coils. A vacuum gap was maintained, crucial for isolating the electromagnetic interactions. Using a motor, the aluminum cylinder was rotated at high speeds, while the coils were energized to create a controlled electromagnetic field. The goal was to synchronize the frequency of the incoming electromagnetic wave with the rotational frequency of the cylinder. When this critical threshold was met, the team observed a dramatic amplification of the input signal. Initially, the signal injected into the system was extraordinarily weak, far below the power of an average radio wave. However, after interacting with the rotating structure, the returning wave was found to have gained significant energy. This amplification provided concrete, empirical validation of the superradiant effect. The experimental observations aligned almost perfectly with the predictions derived from black hole physics. Taking their experiment further, the researchers investigated how the system behaved without any external signal input. They let the cylinder rotate without sending in electromagnetic waves from the outside. Remarkably, the system spontaneously generated its own signal. Over time, This internally generated signal grew exponentially, reaching intensities that damaged the system's components. Specifically, the resistors began to overheat and fail. This runaway energy buildup offered a small-scale but striking parallel to the black hole bomb scenario described in theoretical physics. Throughout the experiment, data was recorded using high-precision oscilloscopes and underwent rigorous time-frequency analysis. In multiple tests, the output energy exceeded the input by a factor of 10 or more. This confirmed that the rotating system could act as a kind of energy amplifier, harvesting rotational energy and transferring it into the electromagnetic domain.